Hello everyone. We'll be starting with the third session of astrophotography learner space. Let's get started. So yeah. So how do we know what stars are made up of, or how far away they are, and whether they have planets without ever leaving Earth? The answer is just light. And today we are going to learn how to read it. So for the third session, we'll be learning about photometry and spectroscopy. So let's get started. So before we analyze starlight, we need three fundamental quantities. Think of them like language astronomers use to describe how bright stars are and why. So first we go for luminosity. That it is the total power that the star radiates in all directions. It's intrinsic. It doesn't matter where you are standing. The luminosity of the star is fixed. The luminosity is basically how much energy a star pumps out every second in watts, just like a light bulb. A 100-watt light bulb and a 100-watt star are essentially the same idea. The formula comes from treating the star as a sphere. So we multiply the surface area 4 pi r square by the flux at its surface. This is the star's true brightness. Luminosity doesn't change with distance, it's a property of the star itself. Next, we move on to radiant flux, which is the luminosity divided by the distance squared. So this is the energy hitting per 1 square meter of a detector, as you can check the units here. This is what your telescope actually measures. Flux is what we observe, the brightness that reaches us. And here's the catch. The further away the star is, the dimmer it appears. Because that same energy is now spread over a much larger sphere. Double the distance, the flux drops by 4 times. This is the inverse square law as you can see here. That's why nearby stars look bright even if they are intrinsically faint. So now there's a quick analogy. If a torch is pointed to you at a distance of 1 meters versus 10 meters, the same torch, very different brightness hits your eyes. So next we move on to magnitudes. And so now what are these magnitudes? It is a measure to to check how bright the or how relatively bright the stars are from each other. So M is the apparent magnitude and capital M is the absolute magnitude. So since we are talking about apparent magnitudes here, we will use flux because flux is the apparent intensity that reaches us. And for capital M, we use luminosity. So for if M was compared here for two stars, we would write L2 by L1 instead of the radiant flux here. But we don't emphasize on capital M here because it's mostly of no use because this is not the intensity or brightness that we perceive. This is the brightness or intensity difference that we perceive between stars. So m depends on this small m depends on distance and capital M doesn't. So the big picture here is the star emits luminosity. It is fixed and intrinsic. It travels through space, spreads over the area 4 pi r square. Then we receive the flux. That's what telescope sees, and we compare fluxes. So yeah. So now let's move on to data reduction and instrumental effects. So your telescope and camera isn't perfect. They add unwanted signals on top of the real starlight. Data reduction is the process of removing all of that garbage. So all you see is just the scientific data that you need. So first, we will be talking about gains. So what is gain? It's the conversion factor between physical electrons collected and the number your computer records, that is ADU. The full form is written here, analog to digital unit. When a photon hits your CCD or CMOS sensor, it knocks out an electron. But your computer doesn't just store electrons, it stores numbers called ADUs. Gain tells you how many electrons equal one ADU. A gain of 2 means 2 electrons gives out one ADU. Now the fundamental problem here is higher gain amplifies your signal. It does that, but it also amplifies noise. So CCDs have one gain value for the whole chip, clean and uniform. And if you remember the concepts from the first session, CMOS has electronics for each and every single pixel. So there is individual gain per signal here as well, which introduces something called FPN or fixed pattern noise here. It is a structured, repeatable pattern of brighter and darker pixels. So fundamentally, gain is not better when higher. It's basically a trade-off between sensitivity and noise. Next, we have dark current. So this essentially is electrons generated by heat inside the sensors and not by photons. So in assignment questions, you must have seen separate folders, and one of them was the dark folders. So what essentially are the dark frames and why do we need them? So so the sensors are warm, and since it's warm, it emits electrons, even with no light hitting them at all. So when we take a 5-minute exposure of a galaxy, your pixels collect two things. Real photons from the galaxy that we tend to observe, and also the fake electrons that are generated due to the thermal current here. So as we just discussed, even in complete darkness, the sensor generates electrons. This is the dark current. It fakes signal that isn't there, and we don't need it. On CMOS chips, this occurs as column FPN, vertical strips across your image. You remove it by taking dark frames. Exposures, and what are dark frames? These are exposures of equal length with the lens cap on. We subtract this from the light frame and then the thermal signal cancels out. So it's like trying to hear someone whisper in a room that's already humming. But you can't reduce the hum or the noise, but you can never fully eliminate the noise it carries. So you take a dark frame, same exposure length, same temperature, lens cap on, zero real photons can enter there. So everything the sensor records is pure thermal noise. So what we do is we just subtract it from the final image and we get the galaxy signal we desire. The thermal patterns cancel out there. So I hope we are clear about dark frames. Next, we move on to flat fields or field currents. So you must have also observed something called flats, a folder called flats with several FITS files inside it. So what is it actually? So calibration frames that correct for uneven pixels sensitivity across the sensor. So not all pixels respond equally to light. Some are slightly more sensitive, some less. There are also dark corners and dust on the sensors causing unwanted noise. So flat fields fixes all of this. You picture a uniformly lit surface. What we do as uh, a solution to this is we picture a uniformly lit surface, a white wall or a light panel, and every pixel should read the same. The ones that don't reveal the sensitivity offset are less sensitive, and the ones who reveal more than that are more sensitive. You normalize this frame to its mean value, then we divide the science image by it. Now all pixels are on equal footing. So why are we dividing here and not subtracting like dark frames? So because sensitivity variation is multiplicative. A 10% less sensitive pixel values always reach 10% low regardless of how bright the source is. Now, when I talk about subtraction or division here of images, what I mean is subtraction and division of the pixel values itself. So let us understand this with a bit of an analogy. So imagine you have 100 buckets collecting rain. Ideally, all buckets are identical, same shape, same size. But in reality, all the buckets can't be identical, like exactly the same. There will be some difference in sizes. Some will be slightly bigger and some will be slightly smaller. If it rains equally everywhere and one bucket collects less, it doesn't mean it didn't rain equally in each bucket. It meant there was a difference or faults in the sizes of the buckets. So camera pixels are just like those buckets. So you test them, you point the camera at something completely uniform, just as we discussed, like a blank wall, and the pixels which read lower than the average are less sensitive, higher than the average, more sensitive. Now you map every single pixel's sensitivity bias, and now that is the flat frame. We divide it by the pixels of the original image, and we get the desired image that we require. Next, we move on to biases or offsets. This is also one of the folders that you might have observed while doing the questions. So what is it essentially? It is a fixed electronic pedestal added to every pixel readout to prevent negative values. It is basically added to every single pixel so that we don't get negative values. So electronics give out analog outputs. So voltages may fluctuate. To make sure no pixel ever reads a negative value, a fixed voltage offset is added to every single pixel before readout. This is the bias or offset. Dark pixels physically shielded from light, measure their difference voltage. So you subtract it from your science frame when exposures are very long or the environment is very warm. The offset can drift, so it is sometimes adjusted manually. So what we do, the entire process of this is we have a raw frame, we subtract the biases and the dark frames, and we add the flat corrected images, and we have the image which is ready for our observation and studies. So yeah. So now, why do we even do photometry? Yeah.
Can you please explain difference between darks and biases?
Okay. So what did you not understand here?
So dark frames also capture thermal noise, right?
Yes.
So and biases is also like compensates for thermal generated voltage. So like why do we need to subtract bias again when we have subtracted the dark?
No, no, no. Darks and biases are fundamentally different because the main reason why we require dark frames is because of the thermal noise that is created by the virtue of the telescopes. But biases do something completely different. It ensures that so computers can't read negative values. So if we have negative values, so what it does is basically corrects those negative values and adds a basic number to it so that the computer can read it and give us a readout image which we can observe and use for scientific studies. So like they are completely different things here. So what you have to understand here is the pixels. Nowadays we use CMOS sensors and every pixel has its own electronics. So if it has its own electronics, then voltages will fluctuate, and it is definitely possible that we might get negative readout values, and we don't need that. computers cannot read negative readout values, and that's why we require biases. They are fundamentally different. Have you understood?
Yes, thank you.
Okay. Yeah. So now let us move on to applications of astronomical photometry. So why do we even do photometry? Here are four real things that astronomers use it for. So first is stellar evolution. Some stars aren't constant. They pulse, getting brighter and dimmer in a regular rhythm. By just watching how a star's brightness changes over time, you can figure out how massive it is and how big it is. So certain star called Cepheids breathe. What I mean by breathing is they expand and contract on a fixed schedule. The cool thing is how fast they pulse is directly linked to how luminous they are. So just by watching the brightness go up and down over a few days, you can get the star's mass and size for free. No spectrum needed, just the light curve. Somewhat similar to the concept of pulsars that we studied in the first session. So why it matters and why it's pretty awesome is because Cepheids were literally how we first measured distances to other galaxies. Hubble used them, and it's mentioned here Cepheids. Next is exoplanet detection. When a planet passes in front of its star, it blocks a tiny bit of light. Photometry catches that dip. So imagine a mosquito flying in front of a stadium floodlight. From far away, you would barely notice. But if you had a sensitive enough detector, you would see a tiny drop in brightness. That's exactly what we do with exoplanets. The star dips might be just 1% for a few hours. The depth of the dip tells you how big the planet is. How often the dip repeats tell you how far the planet is from the star, because we can study the period of revolution and stuff. So Kepler found thousands of exoplanets using exactly this phenomenon, pure photometry, and no fancy equipment was required beyond a good camera. Next one is also pretty awesome, galaxy classification. Galaxies have different shapes and different brightness profiles. Photometry maps how brightness is distributed across a galaxy, which tells you what type it is. So, spiral galaxies have bright cores that fade gradually outward. Elliptical galaxies are smooth blobs of uniform brightness. By measuring how brightness changes as you move from center to edge, called surface photometry, you classify a galaxy without even taking a spectrum. Color also helps. Old ellipticals look red, young spirals look blue. Next one is cosmology. So photometry helps us map the large scale structure of the entire universe, where galaxies cluster, where there are voids, and how the universe is expanding. So this is the biggest application essentially. When light from a distant galaxy travels to us, the universe expansion stretches it. It shifts redder. By doing photometry across multiple color filters, you can estimate how redshifted a galaxy is without actually seeing its full spectrum. Doing this for millions of galaxies, you get a 3D map of the universe where everything is and how far away it is. That's how we know the universe has a web like structure with giant filaments and empty voids. So let us summarize it. So first application was stellar evolution. What we measure here is brightness over time, and what we learn is the star's mass and size. Next is exoplanet detection. So what we measure is tiny brightness dips. What we learn is the planet size, the orbit, its period of revolution. Next we have galaxy classification. What we measure is brightness distribution and what we learn about is galaxy type and age. Next, and the most important, is cosmology. What we measure is color-based redshift, and what we learn is the universe's structure. So the next thing is very important, and we move on to the techniques of photometry. So the first one, as you can see here, is aperture photometry. So what we do here essentially is we draw a circle around the star, add up all the light inside it, and subtract the background star. So let me explain. So the white circle right here is the star, and the reddish circle that you observe here is the aperture, the region that you are summing up. And this annulus right here, this ring-like structure right here, is the region around the star that you are using to estimate the sky background. So the formula here is the so this summation right here is the sum of all pixel values inside your aperture, inside this red circle. And what we are subtracting it by is n stands for the number of pixels in your aperture, and b the average background pixel value that we have. So that we can subtract the background pixel values and actually observe the brightness around the star instead of unwanted noise. So think of it like measuring rainfall in a bucket. You put the bucket under the star, you collect everything, but some of it is just ambient noise, the sky background, not from your star. You measure the noise separately from a nearby patch of empty sky that is the ring shaped structure here, then subtract it. Then what we are left with is purely the star. So there are certain limitations to it. That is, if two stars are close together, the circles might overlap like this. So you can't cleanly separate them. That is why this method is not viable if we are working in crowded fields like the center of a galaxy or a dense cluster of stars. So to fix this, we have another method called the PSF photometry. PSF stands for point spread function. The idea here is instead of drawing a circle, you build a mathematical model of exactly how your telescope smears out a star's light. Then fit that model to every star in that image. You might have observed that instead of circles, I drew ellipses here because this is more accurate. Because of the stretching of the starlight, we observe elliptical blobs instead of perfect circular structures. So now let us first understand, why does a star smear at all? So first reason is the most obvious: diffraction. Light bends around the edges of your telescope, mirror or lens. The next is atmospheric turbulence. The turbulent air blurs the light before it even reaches you. So a perfect point source ends up looking like a fuzzy blob. The blob shape is the PSF, right? That is the point spread function. So the elongated layer blob is the PSF shape. So we have depicted here to be stretched as an ellipse and not a circle, because this is more accurate right here. So imagine you are trying to figure out how many people are there in a crowded photo where everyone's blurry. Instead of just counting blobs, you learn exactly how one person looks when it is blurred by your camera. Then scan the whole photo fitting that template. That is PSF photometry essentially. You know the blur signature, so you can unmix even stars that are nearly on top of each other. So the reason why it works better for crowded fields, unlike aperture photometry, is because As we know, the PSF shape, it's a symmetric blob that's brightest at the center and fades outwards in a very specific known way. Now, if we have two overlapping stars and the combined blob would look very weird and elongated. So the software says essentially is I know every star might look like this specific shape. So let me try placing two copies of that shape at different positions and brightness and see if their sum matches what I'm seeing. It's basically separating it and identifying if we sum those two up, the we get the elongated blob structure that we observe. So let us do a quick comparison between aperture photometry and PSF photometry. So here the method is we sum up the pixels in the circle, but in PSF photometry we fit a model to the star. We assign a model to a particular star. Aperture photometry is best for isolated stars, and PSF photometry is best for crowded fields. So it is simple to use, but it is a bit more complex. For crowding, it fails, and for crowding, it is the best method out there. So the rule is if the stars are well separated, aperture photometry is fine, but if they are crowded, you must use PSF photometry. So now we are done with photometry and we move on to spectroscopy. So what photometry does is it tells you how bright a star is. Spectroscopy splits that light into its colors and tell you what everything else is. So what the spectrum reveals is first temperature. Hotter stars peak at blur wavelengths, cooler stars at the redder ones. Just from the color of the peak, you get the surface temperature. Next, composition. Every element absorbs light at very specific wavelengths, leaving dark lines in the spectrum. Hydrogen has its lines, helium has its own, iron has its own. It's like a fingerprint. You match the lines to the element. Next is the line of sight velocity. If a star is moving towards or away from you, those fingerprint lines, as we discussed in composition, shift. Moving towards you means lines shift blue, and moving away means lines shift red. This is the Doppler effect, and it's how we measure if stars are orbiting each other or how fast the galaxies are flying apart. So basically, photometry gives you the brightness, and spectroscopy gives you the story of that light. So let's understand the principle of operation. So you take starlight, you smear it out by wavelength into a rainbow, then read off the intensity at each color. So let's go step by step here. So first the light enters the instrument and hits a dispersing element. We will understand this entire thing using the LRIS spectrograph setup is. Let me first give an overview right here. So the light enters and hits a dispersing element. It can be a prism, grating. So then it spreads out the light into a spectrum. This lands on a detector as a 2D image. One axis is the position, the other axis is the wavelength. Now we collapse that 2D image into a 1D plot. That is the intensity versus wavelength plot, the actual spectrum that we are going to study. And at last, we calibrate it. So what calibration does essentially is it makes our measurement trustworthy and um, it converts the pixel values into actual wavelength values and readable values that we are going to observe. So in wavelength calibration, we shine a lamp with its known emission lines to map the pixel position to its exact wavelength. And for flux calibration, The detector records the ADU counts. We observe a standard star of known brightness to convert the raw counts into real physical units. So now we will understand a realistic setup that is used in spectroscopy, that is the LRIS spectrograph setup. So LRIS is a real spectrograph on the Keck telescope in Hawaii. The so we will walk through its components in order to understand how light travels through it. So first things first is the slit mask. When the light first hits it, a narrow slit that only lets in light from a thin strip of sky. This defines how sharp your spectrum will be spatially. Wider slit will allow more light and it will blur the spectrum. Next, we have collimator. Light coming out of the slit is diverging. It is spreading out. So what the collimator does essentially is it is a lens or a mirror that takes the messy diverging beam and makes it perfectly parallel. You need parallel light before you can disperse it cleanly. Next, we have the dichroic. It is a fancy beam splitter. It reflects blue light one way and transmits the red light the other way. So LRIS simultaneously captures blue and red parts of the spectrum on two separate detectors. No information is lost here. Next, we go for grating or grism. So what grism is it's grating plus prism. So this is where the actual dispersion happens. The parallel beam hits a finely ruled surface, the grating, or a combination of prism plus grating, that is the grism, which bends each wavelength by a slightly different angle, spreading white light into a spectrum. So at last we have the CCD detector. It records the final 2D dispersed spectrum. LRIS has two CCDs, one for the blue channel and one for the red channel, because no single CCD is equally sensitive across the full wavelength range. So let us understand the full light path in just one line. So first, light comes from sky, it hits the slit, then it goes to the collimator so that it becomes a parallel beam of light. Then the dichroic, so which reflects the blue light one way and transmits the red light the other way. Then we have the grating or the grism where the dispersion actually happens, and then we have finally the CCD detector which records the 2D dispersed spectrum. So the last thing that we are going to cover today is the spectral extraction and calibration. This is what tells you what to do after you have taken the spectrum. Till the last slide, we understood how to take the proper spectrum, which is capable of giving us information that we want to study. So, after achieving the spectrum, we turn the 2D image into actual usable science data. So, the first is filtering the 2D spectrum. So your raw output is a 2D image. We need to squish it down to a 1D plot because it's the easiest to study. But first we need to clean out the sky background a bit because when light came from the slit mask, it is not necessary that only the starlight was measured. Light also could have come from the sky background above the star and below the star. So we need to fix the problem of the sky background again. So our raw output is a 2D image and we need to squish it down to a 1D. So remember from the last slide, the spectrograph outputs a 2D image where one direction is the wavelength and the other direction is the spatial position where on the slit it is. So our star appears as a bright horizontal stripe with sky background rows above and below it. So the spectrograph, as I have mentioned earlier, has a slit and light from the entire slit hits the detector, not just the star. So what we do here is we essentially subtract the background rows from the star rows. Now only the star's signal remains. Then we collapse all the star rows together into a single 1D spectrum, of the intensity at each wavelength. So how it is like is, for example, this is the sky background which comes from the light from the above the star that we have, and then we have the spectrum that we observe, and then again the sky background from the light which comes from below the star. So this is how it looks like, and we subtract uh, the light which comes from above the star and below the star, and we only keep this, and we collapse it into a 1D spectrum, that is the intensity at each wavelength. So the next steps are the calibration of flux. I've divided into two steps. So the simple version is our spectrum is currently in meaningless camera units, ADUs. You need to convert it into real physical units, that is the actual energy per second per wavelength. So what we do here is we observe a standard star, a star whose true spectrum is already precisely known from previous studies. We observe it the same night, same conditions, same instrument. Then we divide our target's raw spectrum by the standard star's raw spectrum. Then we multiply by the known true spectrum. So what we are doing here is essentially the calibration that we have done when we study measurements and units. So the standard star acts like a ruler here. So you know exactly how long it is, so you use it to calibrate every other measurement. The division cancels out the instrument's errors, the camera's color sensitivity biases, the telescope's efficiency at different wavelengths, leaving us with the real flux density. Next is the wavelength calibration. So right now our x-axis is just pixel numbers. You need to convert pixels to actual wavelength in nanometers, which is the final step here. So we shine calibrated lamps into the spectrograph. These lamps emit light at very precisely known wavelengths. These are fixed by physics and they never change. Their emission line appears at specific pixel positions on the detector. So you map the pixel values and then we fit a curve through those points. Now every pixel has a wavelength. It's like getting a ruler with no numbers on it, then putting known reference marks on it. Once you know where the 10 centimeter or the 30 centimeter are, you can figure everything out in between. So let us understand the full summary here. So we have raw image, which is in 2D form. We subtract the sky rows from it. We achieve the raw spectrum, which is the intensity versus pixel. Then we do wavelength calibration. Then we get the spectrum. Then we do flux calibration with respect to the standard star, and we receive the spinal spectrum. So the final spectrum that we have received is what astronomers actually analyze. It is the true brightness of the star at every single wavelength. So does anybody have any doubts until now? So if anybody has any doubts in the data sets that we have given as assignment, you'll also get one data set today as assignment and some theory questions as well. So we will take it up in the doubt session. If you want me to process it from scratch as well, we can do that. And then we will have the final session in of SHO ballots and processing. So if you don't have any doubts, you can leave the meet.